I'm going to do a screencast of my messing around with problem 1, the splitting of the triangle into small triangles which are congruent or similar. And the problem arose from a book by Alexander Seufer called How Does One Cut a Triangle, which is referred to in the Cuoco article on habits of mind. So as I do it, I'll try and highlight some of the habits of mind that I think are important in playing around with the problem. So the problem starts with one triangle cut into 4 smaller congruent triangles using the midpoints of the sides. One of the things that it might be important to do first is to use some deduction. So in the Cuoco article, he says that students should mix deduction and experiment. A little bit of deduction will show that these 4 triangles are in fact congruent. And we can use the midpoint theorem to say that if this point is the midpoint of that line segment, this point is the midpoint of that line segment, then this segment is parallel to this and half the length, which therefore makes it congruent to this. It makes these angles equal. It makes these angles equal. It gives us congruent triangles, and so on. So the question is, how many other congruent triangles can we make if we cut this? The first thing, of course, that springs to mind is to extend. Again, a Cuoco habit of mind. A very simple extension of this says that we ought to be able to do exactly the same thing to each of these 4 triangles. So using GeoGebra, let's do it. We find the midpoint of this line segment, the midpoint of this line segment, the midpoint of that line segment, and we construct a triangle through this point, and this point, and close it back up. You can see that we now have 4 smaller congruent triangles on top. We could repeat this in this bottom left triangle, in the middle bottom triangle, in the bottom right triangle, and we would have 4, 8, 12, 16. We could repeat it again in each of those 16 and get 16 times 4 is 64, and repeat it again, and so on. And that clearly is going to give us 4 to the power n congruent triangles. Of course, the question remains, are there other numbers possible? But before we do that, I'm going to try and look a little bit at the second question. So one of the things that Cuoco doesn't say is that students should be observers. But once you do this, you actually observe something. You observe that there are 4 small triangles at the top, 3 larger triangles at the bottom, or we have 7 triangles altogether, which are clearly all similar triangles. You can see that GeoGebra is nice because you can move points around and you can see that they remain similar. We have 7 smaller, similar triangles. We could then, of course, do this and get some more midpoints of this segment and this segment and this segment. Repeat our triangle construction. And we now have 1, 2, 3, 4, 5, 6, 7, 8 small ones and 2 slightly larger ones, which is 10. We might note that each time we cut a triangle through its midpoints, we obtain from that one triangle 4 new triangles, so the number of triangles increases by 3. Therefore, we can obtain any number of similar triangles from 7 upwards, adding multiples of 3, or in other words, 3n plus 4. And just to write this out, I'll bring up a little Word document. This is something I've prepared before, which shows that we can get 4 to the power n congruent triangles and 3n plus 1 similar triangles where n is greater than 1, because if n is equal to 1 we actually get congruent triangles instead. Of course the question remains, and I'll record this as a second screencast, the question remains, what other numbers of congruent triangles or similar triangles can we get?